gravitational potential energy, or at least as far as Newton is concerned. Launching straight into it. Previously, we have used the simple formula the textbook in a lot of places use a big U for gravitational potential energy. Not the biggest fan. So previously we've used this to find gravitational potential energy. Now, of course, if I was plotting energy versus gravity there, that in fact would be a straight line. So the formula assumes that gravity is linear. But as you already know, gravity is a point source in 3D space, radiating as spherical shells. So gravity varies with the inverse square. It's an inverse square law. Let's get a straight line. How's that? Was the inverse square of the distance. All right, so now previously we used a combination of Newton's second law and Newton's universal law of gravity to calculate the acceleration due to gravity of any planet. And of course, here at Earth, we find that that ends up being 9.8. So previously we calculated the value of G for any planet, for any body. It could be a moon. By equating Newton's second law with, let's abbreviate it, Newton's universal law of gravity. That is, we had Newton's second here, and assuming big M is the planet, little m is your test mass. It's an inverse square law. And if we did that, we end up with G equals M on R squared. So now, if we take this and substitute it into this, we should get to where we want to go. So if we substitute this inverse square relationship, all right, inverse square relationship into our previous formula for gravitational potential energy, this one, we get that the potential gravitational energy should look something like this. Big G for the gravitational constant, m on r squared, h, and that cancels with that. And can I tidy it up a little bit if I put the big G at the front? Big M, little m on R. And we say we're letting R equal H. That is, we're taking it from the center. All right, so far, so good. So next, we need to pick a good 0 point. We need to choose a good point for 0. Now, if you're doing multi-body analysis, picking the center of any one body makes things difficult and a little arbitrary. So it's easiest and makes the most sense if you pick infinity to be a 0 point. So it is easiest when we choose a point at infinity, or let's explain what infinity is. Could be infinite anything. If we choose a point at infinite distance, to be 0 potential. Oops. Full stop. So clearly, if infinite will be it'll be the highest value, highest possible value for the gravitational potential. Clearly is spelled wrong. Clearly, infinite is going to be the highest possible value for gravitational potential energy. It's the highest value because it's the highest point. You can't get any higher than at infinity. And so if it's 0 and it's the highest, every other value must be negative. So if the maximum is 0, all other values will be 0. I mean negative, which is what I said. Will be negative. So this gives us a formula of the form minus gravitational constant, big mass, little mass on R, which is what we had here, with a minus sign. That's probably worth highlighting. Oop, come on. There we go. So there we go, an expression for the gravitational potential energy of a body. It's important to understand it's got to be a minus because, especially if I'm going to talk in terms of, it's naturally going to fall from high potential to low potential. So the work that I would have to do on a body in order to move it is effectively negative. All right, so now, oops. So as you would have looked at in prelim, we have this concept of mechanical energy. It's a bit of a fairy tale concept, but it's stating that a body under ideal conditions, the sum of the gravitational potential energy and the kinetic energy is some constant. And so it's sometimes useful to think of the same in terms of orbiting bodies. So for the notes, as we have seen earlier, it is sometimes useful to consider the concept of mechanical energy. And that is, if I let EM be mechanical energy, as I mentioned previously, it's the sum of the gravitational potential energy plus the kinetic energy. I'm going to do some manipulation here, so let me call that one 1. We know that the kinetic energy is half mv squared. Now the v squared is interesting because it also appears in our formula for our centripetal acceleration or centripetal force. So we can use that to find out what that v squared would have been, or is. And to find v squared, let's use our formula for centripetal force, mv squared on r. Newton second. We've done this before. Just trying to think if I'm going in the right direction. No, it's not what I want. Let me take a few steps back. I don't want Newton's second. I'm trying to find an expression for v squared. I need to equate that to Newton. We're talking about Newton's gravitational potential. Newton's gravitational potential energy. Yeah, this is going to work. So let's equate these two. They cancel, and that cancels with one of those. And so I'm left with v squared equals gm on r. Okay, good. So I have an expression for v squared. So now, if I place this one back into here, so 3 into 2, kinetic energy is half m. Here's my expression for v squared, gm on r. And not much to do there except to just tidy it a little bit. Big G, big M, little r on to r. So that too is probably worth noting. And when you look at that compared to this one, GMM on R, this is GMM on 2R, it's worth noting that it's half the magnitude of this thing. The gravitational potential energy. All right, now, if I take this one and I place it all the way back into my first equation, so it's EK, I substitute into here. Number 1. Then I have EM because of that EG. And this expression now for EK, now just to label the point, I'm going to pull that half out because of this, right? This EG is here, minus big G, big M, M on R, plus half of big G, M, M on R. So it's minus 1 plus a half of this blob, which is minus half of that. That's minus half of this thing. So the total mechanical energy of a satellite can be expressed as such. All right, so we have the total mechanical energy, and along the way we found expressions for the kinetic energy and the gravitational potential energy. All right, so let's have an example. Now, last lesson I mumbled something about Australia's first geosynchronous satellites and the fact that it was sold to Optus, and that was about all I could recall. I since looked it up. They were called OSAT 1, 2, and 3, or A1, A2, and A3. Launched in 1985. Well, the first two were in 85 and the third one in 1987. They're only meant to have they're only designed to have an 8 to 10 year service life. But the A3, the third one, was decommissioned in 2008. So from 87 to 2008 is 21 years. So it sets some kind of record for being a long-running satellite of this particular type. As you can imagine, with the pace of technology, 21 years is a long time. It must have been quite old and rickety by the time it was actually taken out of service. So, looked up the stats on these things, and they're actually 654 kilos. So, as an example, let's take the first OSAT satellite, launched in 1985. So if we just examine a geostationary satellite of 654 kilograms, not small. Not small. So let's look at the gravitational potential energy first of what that might be. So minus G M on R. From last lesson, you recall that the altitude was 35,786 kilometers. So the altitude, 35,786 kilometers, so times 10 to the 3 meters. We're going to need some more constants here to help us along the way. We need to add to that the radius of the Earth. So the radius of the Earth, 6.371, the average radius of the Earth, by 10 to the 6, so 6 million meters. We're going to need the mass. It's terrible. How do I draw M's? I don't know. I've lost the ability to write. It's late in the day. 5.972 by 10 to the 5.972 by 10 to the 24 kilos. We're going to need the gravitational constant. That one's easy. 6.67 by 10 to the minus 11. The units are harder though. You've got to think in terms of the formula and turn it upside down, kilograms squared, because I've got two masses multiplied by each other. All right, and do we need anything else? Eventually, we're going to probably need the time taken for the sidereal day. So the sidereal day was 23 hours, 56 minutes, 4 seconds. And looking back to last lesson's notes, that was 86,164 seconds. All right, let's return to the problem at hand. So the gravitational potential then, minus 6.67 by 10 to the minus 11 times the mass of the Earth, 5.972 by 10 to the 24 times the mass of the satellite, which is 654, all over the radius. And its altitude is 35,786 kilo. And the surface of the Earth is 6.371 by 10 to the 6 from the center. And if I used my calculator correctly earlier, it's minus 6.18 by 10 to the 9. That's a 9. 10 to the 9 joules. Or for the engineers, 6.18 by 10 to the 9 is gigajoules. All right. A lot of gravitational potential energy. You can imagine if it fell out of the sky and hit you on the head, that's not going to tickle. All right, so next up we could look at the kinetic. Note that it's half the magnitude of Eg. So, well, that becomes easy. It's half this magnitude, and it's positive. So it's 3.09 times 10 to the 9 joules. I feel the need to serif my J at this point. 3.09 by 10 to the 9 joules. Yeah, that's right. I feel the need to appease engineers. 10 to the 9 is giga. Don't waste time doing this in an exam, by the way. Just give it in scientific notation. 3.09 gigajoules. All right. So if we wanted to examine the mechanical energy, which is the sum of these two, well, it's just going to be the negative. It's going to be the negative. Can I write this in a clever way? Eg on, hello pen, Eg on 2 which is minus 3.09 gigajoules. All right. So done piecewise, it's not particularly difficult because this relates directly to that, which is half of that, or half of the absolute value of that. Easy peasy, as long as you can press all the right buttons on the calculator. What's a little more difficult is being asked to find the velocity. So if we examine the velocity, now you could just do it as distance over time. So let's do that first. Velocity, of course, is the distance, which is 2 pi times the radius, the circumference. The radius, which I wish I'd written down now. Let's add it. Let's work it out again. 35,786 by 10 to the 3. This is the average radius of the Earth all over this 86,164 seconds, our sidereal day, right? So the distance around the circle divided by how long it takes to get there. Looking up the earlier result, 3.07 by 10 to the 3 meters per second. Nicely to 3 significant figures as well. So 3,000 meters per second, 3 kilometers per second. Not too shabby. And I think from last lesson, the low Earth orbit, we calculated to be, was it 7 or 9? 7 kilometers per second at 2,000 meters up. But of course, we can use energy to get us there. So now, right, so you need to know that in order to work that out. If you don't, or you're in a different situation, or you don't want to have to work that out, you can, of course, use the expression for energy. So now, via the kinetic energy, write it separately. Of course, that's half of the mass times the velocity squared. Oh, and of course, we have the energy, kinetic energy we worked out earlier. It's 3.09 by 10 to the 9. 3.09 by 10 to the 9. So if I rearrange this equation, I get V equals the square root of, I need to take 2 lots of that one, 2 times 3.09 by 10 to the 9. And I need to divide by the mass, which we're told, which I looked up, was 654 kilos. Put in orbit by the space shuttle. The first 2 were put up by space shuttle, and the third one was by the Ariane rocket. Don't we all miss the space shuttle? We pin our hopes on Elon. All right, so 2 times the value for the energy divided by the mass, which I've forgotten in my excitement. 654 kilograms. And with any luck, you'll get the same result as earlier. 3 significant figures. All right, so energy calculations can have their uses, but not always necessary. Not necessary. All right, well, that does it for this lesson. I'm Keith Johnston. Thanks for watching.